Okay, we are starting chapter 5. 5.1 is using trig identities. These are basically just properties we can use to simplify more complicated problems. The idea behind an identity is, well, let's just look at a basic example. So like solving the following equation here. X plus 3 equals 4. We all know we can subtract 3, both sides, and we get 1. We know this is true. Only x can be 1 in this situation. On example B, though, we can actually combine these and get 4x equals 4x. You can even divide by 4. You end up with x equals x. So this is a unique situation where not only is it true for just one number, it's true for all values of x. And this is what we call identities, when it's true on both sides, no matter what we plug in. When we look at trig identities, we're looking at a statement of equality between two expressions that is true for all values of those variables. Here are some of the most common trig identities we are going to come across. And you actually have already seen these. These are reciprocal identities. We know that if we have sine, that's the same as 1 over cosecant. And vice versa. Cosecant is the same as 1 over sine. So here's all your reciprocal ones that we're already familiar with. This makes certain problems very easy. Like if I see cosine of theta equals 3 over 5, then secant, well, those have a relationship. They are reciprocals. So secant would have to be the reciprocal. So it would have to be 5 over 3. Okay, so that's something we're already familiar with. Here's some of the newer ones, although we have seen this one. This is a very common one. When tangent of theta is equal to sine of theta over cosine theta. We use this in our unit circle. When we were looking for tangent, we did sine divided by cosine. A couple other ones are cotangent. Well, it's reciprocal, right? Tangent, cotangent, so cosine over sine is equal to cotangent. Ones you've definitely not seen are Pythagorean identities. As you can see, they kind of resemble the Pythagorean theorem, and that's how they're actually derived. So sine squared of theta plus cosine squared of theta equals 1. That's one of the most common ones. And then we see some other variations of that using the other trig values. By the way, you don't have to memorize any of these. You will be given these on your reference sheet. It should be on one of the first pages of your packet. So you don't need to memorize any of these. You just got to be able to use them. Just for a point of clarification, sine squared, that throws people off because you can't square sine. That's like squaring a plus sign. It doesn't make any sense. When you see this, what really is happening there is the sine of theta squared. So I would take the sine of the angle and then square that value. That's actually what's happening there. That just gets tedious to write with all the parentheses, so they just shortcut it to this. A couple of the other properties are these guys, not as common, but they'll be on your reference sheet or they'll be listed in case you need to simplify something when these pop up. So if they look like this, we can replace it with these identities, these properties. So let's try a couple examples here. The first one is actually kind of going back to things we did in chapter 4. If I have cosine of theta equals 3 over 5, find cosecant. Well, these don't have a relationship. They aren't directly related in any of my identities. None of these here does it pop up, okay? So we can just think back to other ways to solve this. First off, I can make a triangle. Cosine works on right triangles, so I know cosine is the adjacent over the hypotenuse. So let's say I put my angle here, and the adjacent side has to be 3, hypotenuse side has to be 5. If I'm looking for cosecant, I can remember that that's related to sine, and sine happens to be the opposite over the hypotenuse. So I need the opposite side. So I need to find the opposite side here. If you know your patterns, you should already know what this number is going to be. If you're not sure, you can always use Pythagorean theorem to find your missing side. That's just 9. If we subtract the 9, we'll get 16. Square rooted, so x is 4. So my missing side here is 4. And now I have my opposite and hypotenuse. I have both these sides, but that's for sine. I'm looking for cosecant. So cosecant would be hypotenuse over opposite. So my cosecant will be the hypotenuse, 5, over the opposite, which is 4. And there's my answer. So just use some tricks you already know, like making a right triangle, especially when there's not a relationship here. All right. Now we're going to get into the more complicated part, which is simplifying these, and that basically means to put the expression in the simplest form possible. This is using your identities, using the properties to break this down and make it simpler. One of the biggest hints, and we'll talk about many strategies you can use, is to get everything in terms of sine or cosine if you don't see anything else to use. Okay? So look at this first example. What I would see is I've got cosecant, I've got cosine, cotangent. None of those have a direct property that I can see in the list of identities. Cosine times cotangent, for example, that's not listed, that's not a property, so I can't do that. But what I could do is change everything in terms of sine or cosine. That way, if they're all the same, they could hopefully cancel or combine. So cosecant, for example, is 1 over sine. Minus cosine, I'm going to leave alone. And cotangent, if you look back at your properties, cotangent is cosine over sine. So this would be times cosine over sine. And I know what many of you are thinking, this made it a whole lot more complicated. But if you just stop and look at it, we can combine and continue. Can't do much with this 1 over sine, so I'll leave it. But cosine times cosine is cosine squared. Okay. These fractions actually have the same denominator here, so I can actually combine these into 1. So it'll be 1 minus cosine squared over sine. So I have one big fraction here. This is where I can actually alter some of the properties I know of. 1 minus cosine squared looks very similar to another property. Over here we had sine squared plus cosine squared equals 1. So I'm going to use that. If sine squared plus cosine squared equals 1, I can manipulate this property. I can rearrange it. I can just make it into different forms. For example, I could minus cosine on both sides. I mean, I'm just moving it to the other side. It's already equal. It's been proven to be true. So then I have a new property, basically. That would be 1 minus cosine squared on one side and sine squared on the other. This here is just an altered version of this guy over here. Okay, I just rearranged it. It's still equal. It's a property that I can just rearrange. And if you look back to the problems we're working on, this is something we have, so I can replace this with sine squared. So let me go back to my problem here. Instead of 1 minus cosine squared, this can be replaced with sine squared from our property. And if I have sine squared divided by sine, it'd be the same as x squared divided by x. It would reduce it to just sine of x. And then we're done. So we took this crazy, gnarly problem and reduced it to just sine of x. And that's our goal. Don't expect you guys to be pros at that in the beginning. It's going to take some practice. Let's try another one. Cosecant, cotangent. If you look through your properties, we can't do anything with that. That's not one of our given properties. So let's change it around. Cosecant can be 1 over sine. And cotangent can be cosine over sine. And again, that made this problem a whole lot worse. But if you notice, everything's sine and cosine, so hopefully some things will combine. In this situation, we have a fraction divided by another fraction. Well, that's the same as multiplying by the reciprocal. So I'm just taking my fraction and multiplying by the reciprocal. In this case, I have a sign on bottom, sign on top that would reduce. So I'm left with 1 over cosine. If you look back through our properties, this becomes just secant. And then I'm done. Trying to reduce it, typically when you reduce it, it ends up being just 1 trig ratio. That's the goal. One last example, one other strategy to show you when you see a problem like this, I'm trying to simplify. Well, you might use other like algebraic techniques like FOILing. So I'm going to go ahead and multiply this out. 1 times 1 is 1, 1 times sine is sine of x, negative sine times 1 is negative sine of x, negative sine times sine is negative sine squared. So not much better, but we can go further. Sine minus sine is going to cancel out. So I'm left with 1 minus sine squared. And again, go back to our properties. We have a property on our list there that says sine squared plus cosine squared is equal to 1. That's our property. I can rearrange this though. I can move the sine squared to the other side. So I would have cosine squared is equal to 1 minus sine squared. So remember, when any properties you're given, you can rearrange those. So I have 1 minus sine squared in my problem. So 1 minus sine squared can be replaced with cosine squared. And then I'm done. So any of these properties that you see, any of the identities can be rearranged because they're proven to be true. As long as you, obviously, minus to both sides or add to both sides, whatever it calls for. One other thing to note, going back to these properties, is you can also see other versions of them. For example, this guy could also be seen, if I see a tangent squared, that would then be the same as sine squared over cosine squared. And it'd be true for any powers. So you'll see some altered versions like that that also are true.